In this video, we'll discuss integration. And integration is the second main component of calculus. In order to understand integration, I'd like to first talk a little bit about the geometric concept behind the idea. And so to do that, I'd like to look at a couple of simple examples. That is, I've drawn two shapes here, both of which are drawn on the xy plane. And I have two functions. So the first function is y equal k, and the second function or curve is y equal x. Okay, two familiar curves which form two familiar shapes. And they're familiar in the sense that we know the area of a rectangle and we know the area of a triangle, okay, right away. That is, that the area here, if I want to know the area starting at the origin at 0, at x equals 0, and going out to some value x, to compute that area, all I need to know is this length multiplied by the height, because that's the area of a rectangle. And of course, if x gets larger, the area gets larger. Okay, but if we fix our ceiling at this curve here, y equal k, then we can certainly write down a formula for the area underneath this curve, y equal k. Okay, it's just a constant there, y equal k. So we know the area as a function of x, or written in terms of x, is just, again, the width multiplied by the height. Well, the width is x, because we've started at 0, we're going out to length x, and our height is fixed at k, so it's x times k. And over here, we have a triangle. And for a similar reason, we can certainly write down the area function, right, as a function of x. So if I go out to this distance x, then I know the area underneath that triangle. Because I've fixed the ceiling here, the ceiling is the function y equal x, and this x just can move out at some distance, however far I want to go, to make a larger area, just a bigger triangle each time. But we certainly know the area underneath that curve because it's the area of a triangle. The area of a triangle is, of course, 1/2 base multiplied by its height. So we can easily write down a function for the area in terms of x. That is, it's 1/2. The base is, well, I start at 0, go out to x. The base is x. And the height is, we go up to this ceiling here, to this function. So the height is actually x. So 1/2 x times x, or that's better written as 1/2 x squared. Okay, so this is the area function for both of these, underneath both of these curves. Okay, this flat curve and this sort of y equal x curve as a function of x. And I want to show you the relationship between this area and, in fact, the equation of the curve. Okay, so let me write this down. So the line, or the curve, is, in this case, given as y is equal to k. The area, we just determined here, as a function of x anyway, is kx. So I'll call it a for area, is just k times x. Over here, the line, or the curve that I'm talking about, the function, is y is x. And again, we computed the area right up here as a function of x. I'll call it a. It's equal to 1/2 x squared. And hopefully you can see there's already sort of a pattern going on here. That is, there's really a relationship between the line and the area underneath the line out to some distance x in both cases. And in fact, hopefully you can already see one of the connections that we have. That is, that if I go, in fact, in this direction, that is, by that arrow, it's really just the derivative, right? Because we already know derivative. That is, over here, if I take the derivative of a with respect to x, I get k, right? Because the x goes away, I just get a k, which is, of course, equal to y, my line. So the derivative gives you back the line. The derivative of the area gives you the equation of the line under that encloses it, right? That makes it ceiling. Same thing here. If I take the derivative of my a function, well, the 2 comes down. We know from power rule, it cancels the 1/2, and I just get x. So in fact, this a is equal to, the derivative of a is equal to x. So that's equal to the line. So again, if I go in this direction, I just take the derivative. I'll write that as derivative. take the derivative, I can go, given the area, you take the derivative, you go back to the equation of the line. Okay, so it turns out that if I want to go the other way, that is if I'm given the line and I want to know the area underneath the line out to some point x, I have to go backward. And the backward direction is exactly what you might expect it to be called. That is, it's called the antiderivative. You're going backward. Okay? So if I want to go backward, that means I want to go from here to here, or from here to here, from the line to the area. We have what's called the antiderivative. So that was the derivative. This is the antiderivative. Okay, and this is a constant theme. The more of these shapes that we try to decipher, determine the area of, and then find the relationship between that and the curve that encloses the area, the more we'll find that this exact relationship will hold all the time. And in fact, this is precisely what is studied in what's called integration. That is, we're really looking for a relationship between, given some curve, how do I know the area underneath that curve? And the answer is, we want to compute the antiderivative. The antiderivative will give us a way to determine the area underneath any given curve. So this is really the connection we have between the area and the line that is the ceiling of that area, that it sort of encloses that area. So more explicitly, I've written this down again. That is, we started with the function y equal k as the top. That was the constant function. That was what created the rectangle. And the area underneath that rectangle, out starting at 0, out to some distance x, was given by kx. Okay? And similarly, when we started with the function x, okay, that was sort of the 45-degree angle line, and I wanted to find the area of the triangle out to some distance x, starting at the origin, it was given by 1/2 x squared. Okay, we just determined that from the geometry of the problem and the geometry of what we already know. We know the area of a triangle and of a rectangle from before. And this is the connection that we talked about. That is, if I want to go from area to the function, I take the derivative. If I take the derivative of the area, I get the function in both cases. However, what's new here, and what's going to be called ultimately integration, is if I want to find out the area underneath these curves, these functions, starting at 0 out to some distance x, then I want to find what's called the antiderivative. And the antiderivative, all it means is we go backward. Okay, so if we already know how to compute the derivative with some shortcut rules, then all we've got to do is sort of unravel those rules and do the opposite, to go back to what's called the antiderivative. So in other words, if I have a function and I really want to know the area underneath that function, I could easily do that, easily compute that, by finding the antiderivative, which is just the opposite of the derivative. We just go backward. So more formally, the antiderivative is really the function whose derivative gives you the function you're looking for. Okay, we're just going backward. So here's the more precise way of saying it. If the derivative of this capital F gives you little f, then the capital F is really called the antiderivative of that f. So really what we're after is, given some lowercase f, by finding the antiderivative, that means I'm looking for the function whose derivative results in lowercase f.